Human need for air is a constant condition. Living beings rely on the respiration process. The intake of oxygen fuels our cells, breaks down the food we eat into energy, kills bacteria, etc. So that being said, it goes without saying that the quality of the air that we breathe is also critical to our health and well-being. Air ridden with pollutants is detrimental to our health. Upon intake, the air travels through our bloodstream and can expose key internal organs to pollutants. With increased anthropogenic activities, both from sources like operating vehicles, buses, and other modes of transportation, power plants, industrial facilities, factories emitting air pollutants like ozone, nitrogen oxides, carbon monoxide, sulfur dioxide, and particulate matter, which can cause long-term impacts on health. The statistics behind air pollution are enough to provide key, clear insight into the scale of this issue. According to data from the World Health Organization, 9 out of 10 people around the world are breathing air with high quantities of air pollutants. Every year, 7 million deaths are caused by exposure to outdoor and indoor air pollution, and air pollution is linked to strokes, heart diseases, cancers, and both chronic and acute respiratory diseases. That's 90% of the world's population housed here on Earth breathing poor quality air. So the air that we breathe is the fuel to the engine that is our body. But if that fuel is knocking off years from lifespans and increasing risk of diseases and health conditions, it becomes harmful to our best interests. Using a data visualization-based approach to draw out hourly air quality concentrations of carbon monoxide, sulfur dioxide, ground-level ozone, we can mitigate the impact that these harmful pollutants have on health by providing us with key insights into external factors that contribute to increases or decreases to air quality in our environment. So in this video, I'll be drawing out trends through analyzing air quality data collected from an undisclosed city in Italy. These values were collected as responses from a multi-sensor device which is deployed at ground level, but prior to data visualization and going through the dataset, I'll just quickly run through the dataset's attributes to provide some additional context and information into each of the attributes. And then additionally, as a side note, the dataset that I worked with, you can actually find in the description. It was from the UCI Machine Learning Repository. So going through, first up we have the date and time. These are pretty straightforward. They're in day, month, year, and hours, minutes, seconds format, and they just represent the date and the time that the responses were collected. And then we have true hourly average concentration, CO in micrograms cubed. CO also stands for carbon monoxide, and it's a gas that's very, very difficult to be picked up by the 5 senses because it's odorless, it's tasteless, there's no scent to it. But it actually forms naturally through combustion and can be found in very, very, very low concentrations in the Earth's atmosphere. But other sources of carbon monoxide include cars, trucks, vehicles, or other human activities that burn fossil fuels. And then we have PTO8.S1, tin oxide, hourly average incident response. Tin oxide is just created by burning tin metal. And then true hourly average overall non-metallic hydrocarbons concentration in micrograms cubed. Quite the mouthful, but basically non-metallic hydrocarbons, these gases just encompass ethane, propane, isoprene, and basically they're released naturally through sources like fossil carbon deposits and volcanic activity, wildfires. But however, anthropogenic activities such as biomass burning and industrial emissions can also contribute to this. Then we have true hourly average benzene concentration in micrograms cubed. So benzene can actually be found in quantities in outdoor emissions from like gas stations, cigarette emissions, and also from vehicle motor emissions. Then we have PTO8.S2 titania, hourly average incident response, true hourly average NOx concentration in ppb. So NOx also refers to nitrogen oxides, and they're a family of poisonous, highly, highly reactive gases, and they actually encourage the formation of smog and acid rain, and they even play a role in influencing the tropospheric ozone. Then we have PTO8.S3 tungsten oxide, hourly average sensor response, and true hourly average NO2 concentration in micrograms cubed. NO2 actually falls under the broader family of the nitrogen oxides. However, it's specifically included because nitrogen dioxide has a very aggressive impact on health and the environment. And then tungsten oxide, indium oxide, temperature in Celsius, relative humidity, and absolute humidity, which are pretty straightforward attributes. So with that additional context in mind, I'll be running through the dataset and the data visualizations now. So first, importing dependencies, and then using Matplotlib, Seaborn, and Plotly as our data visualization libraries. And then we read in the data frame, and we can take a look really quickly at the head of the data frame. And I also made sure to parse the dates as one column, so that would be easier. So we have the date in the time column, which was just parsed as one column. Then we have df.info and df.shape. df.info just gives some information into the data type of each of the columns, and then the null count. So this time though, the null count actually isn't too useful because each of the values were tagged, the missing values were tagged as negative 200 values, so it wouldn't pick up on that. And then we have the shape of our data frame. So we have 15 columns because we parse the day and the time as one column, and we have 9,357 rows. So some more data exploration, basically describing the data set, taking a look at the count, the mean, the standard deviation, the min of each of the columns. And then I also wanted to take a closer look at CO level because there were only 5 possible instances for that. So high, very low, low, moderate, and then very high. And you see that there's a lot of instances of high and low, but there's not too many for very high. There's only 12 instances for that. And then normally, using isNA.sum would be enough to find the missing values in this data set. However, because again, the authors of this data set have decided to tag the missing values as negative 200, that won't really be helpful in this case. So we're going to have to go through each column and find all the missing values, which are negative 200 values, and then we're going to have to pass our own judgment as to whether we should drop rows or just drop entire columns. So looking through and going through all the columns, we see that most of the columns have 366 missing values, except for NMHC_GT, which has 8,443 missing values. So we can't drop rows because if we were, we would have a lot of missing values. So what we're going to do is we're going to drop the NMHC_GT as a column entirely, and then go through after that and just find all of the drop all the rows that have a single instance of a missing value. Yeah, so just doing that, dropping the NMHC column, and then going through and dropping all the rows with single instances of a missing value, and then checking the new head of the data frame and looking at the shape. And at the new shape, we see that we have 6,941 rows. So more rows were dropped than I would have liked, but 6,941 is still a healthy amount of values to have in a data set, so it's all good. Then we're going to do some visualization, and we can see the distributions. We see that all the distributions have a left shift, so it has a wide range, but most of the values fall on the lower spectrum. And then just some helper functions to help us visualize. I decided to visualize through scatter plots, field area plots, line charts, violin plots, which are really, really helpful for showing distribution, and then displaying heat maps. So heat maps here, I use it to show the correlation between the attributes to help drive more informed decisions for visualization. And we can see that when compared to itself, it has a complete correlation, which it should be because we're comparing something to itself. But then we see for some other things. For example, temperature has a very, very, very strong correlation to C6H6_GT. And then that could be useful information. And then we can see the air pollutant concentrations change over the time span of 24 hours. So here, this is also, keep in mind, recorded in military time. So we see that around 5 p.m., 6 p.m., that's when the air pollutant concentrations start to go up, and then it goes straight up, shoots up at 8 p.m., or 8 a.m., sorry. 8 a.m., that's around the time when most people are starting to get ready for school, or maybe they're driving to work, and then it goes back down, goes back down, goes back down, and then it shoots back up again at 14 in military time. So 14 in military time would be 2 p.m. in 24-hour clock. So 2 p.m., that's around the time that most kids are heading home from school, or adults are on their break, lunch break from work, and then it goes back down, goes back down, goes back up. And then at 18, that's around 6 p.m., and it peaks at 19, which is around 7 p.m., when most people are headed back from work after a long day. Which should explain the increase in air pollutant concentrations because there's more usage of vehicles. And then we have the hourly average air pollutant concentrations over the first day in the data set and over the change over the near end of the last day in the data set. So we can't actually compare these two, but we can see that there is a correlation between this and the first line chart that we visualized. And then we can see a change over an entire week. So we can see that if we were to visualize an entire week, starting at Monday, that's when it sort of peaks, and then it goes down on Tuesday, and it goes back up, and it stays pretty consistent for the rest of the week until we hit Saturday. That's when it goes down, and it goes back up a bit, slightly for Sunday. But we can sort of extrapolate here, and we can say that air pollutant concentrations drop when there is a weekend. So weekends are typically when people stay home, they're not using their vehicles as much as if they were to be on a weekday. So that could explain the drop. Then we can see the change in concentrations over temperature and relative humidity, as well as absolute humidity. We can see the temperature and relative humidity have a negative correlation. The higher the temperature is, the lower the relative humidity is. And then we can also see that for visualizing the scatter plot, the higher the absolute humidity is, the higher the temperature is. Now this was actually really, really interesting. So we're taking a look at concentrations of CO level over the entire year, and we can see that high, moderate, and low have stayed very, very consistent. So high, moderate, and low, they're pretty much dots for every part of the year time span, except for very high. Now, there are only 12 instances of very high anyways. However, we see that the very high dots have a strong correlation to each other, and they exist sometime around the October to December time span. So we could also again extrapolate here and say that when it becomes colder, people are less likely to use vehicles, are more likely to use vehicles, and that could be because it's colder, people are less likely to bike, walk, take public transportation. So going through, we can also take a look at the violin plots we made, which are really great for showing distribution, and we can see that on this violin plot specifically, which was pretty interesting, is that as the relative humidity goes up, the very high violin plot also happens to go back up again, and we also have to take into account that relative humidity has a negative correlation with temperature, which would explain why. And now, so pretty interesting, but first half of the year time span of air quality concentrations. So we see that the air quality concentrations kind of stay the same and stagnant around March to September, but then after that they start to go up. So that's around the colder time of the year, and that's when the NOx/GT concentrations go up again. And then for the second half of the time span, it's kind of the opposite, because it's showing the colder months first. So around the colder months, the air concentrations for NOx/GT go up, and then as it gets warmer, they start to go down again. And then full year time span of air quality concentrations. Now, they didn't display or disclose the city that the air sensor was deployed in, so it's kind of difficult here to extrapolate and kind of like provide a conclusion for why exactly this is. However, if you are from Italy, I'd love to hear your thoughts on explaining these really, really sharp increases and decreases throughout the year for air quality in PTOA_S1_CO, which would be really, really helpful. But next steps for this data set. If we had the actual location of where the air sensor was deployed, I could actually do some more research into the city and then some social norms there, and we can take a closer look into like explaining exactly why the concentrations in air pollutants change so drastically over the course of the year. And then also if they were to provide geographical locations of different, I guess, areas, then we can take a look at the locations on the map, and we can kind of like explain more. For example, if we see a very high increase in I'm trying to remember here, but in maybe benzene, then we can say that that area has a high smoker population or has a gas station there. So we can kind of extrapolate there a little bit more. But I really enjoyed working on this data set, and air pollution is such an important problem to work on because it impacts, again, 90% of the world. But with a better data set, we can make better visualizations and hopefully save some lives.